Hey folks, we're going to continue on with the concept of continuity and working with piecewise functions. But before we do that, I'd like to start with just another example of an indeterminate limit. So the following limit down here says the limit as x approaches 0 of 1 divided by 1 plus x minus 1 all divided by x. First thing you should always try is direct substitution. So if you fill a 0 in for these x's, you'll notice we get 1 over 1, which is 1 minus 1. So you get a 0 in the numerator over 0 in the denominator. This is an indeterminate limit. Okay? Indeterminate means we are going to have to do something to reorganize or to rearrange this actual limit here so that we can get a factor from the numerator and denominator to cancel away, and we'll be able to solve this. There's something happening here that's causing this to make it equal 0 over 0. So let's try and figure that one out. When we have a complex fraction, the best option is to multiply everything by a common denominator. Now, you might be wondering where I got this 1 plus x as my common denominator. All I really did was I took this denominator right here, 1 plus x, this denominator right here, 1, and this denominator right here, 1, and I multiplied them all together. Well, 1 times 1 plus x times 1 gives me 1 plus x. So I'm going to multiply both the numerator and the denominator by 1 plus x. Keep in mind, when I multiply the numerator by 1 plus x, I have to multiply both of these terms. Okay, the first term, 1 over 1 plus x times 1 plus x. Well, these would cancel, and it would leave me with a 1. So I have the limit as x approaches 0 of a 1. This calculation is pretty straightforward. Negative 1 times 1 plus x. That would give me negative 1 minus x. So I've just multiplied this 1 plus x by this negative 1. Negative 1 times positive 1 gives me negative 1. Negative 1 times positive x gives me negative x. In the denominator, I'm going to leave it as x times 1 plus x. Again, I don't want to multiply that out. I want to leave it in its factored form. I'm hoping that some factor in the numerator and denominator will cancel away. And once we simplify the numerator, I think you'll see what is going to go away. So again, it equals the limit as x approaches 0. Remember to write this each time as we move down. So I have 1 minus 1, that gives me 0, minus x gives me negative x, over x times 1 plus x. So this is where I can divide the negative x by the positive x, and it would leave a negative 1. And here is where I can drop the limit notation. I don't need to write the limit as x approaches 0 anymore, because I'm going to go back to direct substitution. So the numerator is going to equal negative 1. The denominator is going to equal 1 plus 0 times 1, which would be 1. 1 plus 0 is 1 times 1 is 1. My answer for this question, or this limit, would be negative 1. That function intends to reach a height of negative 1. So there's an example of where multiplying by a common denominator will get rid of your complex fraction. And it also gets rid of my indeterminate form. Okay, now I just want to take a look at another piecewise function, and we'll investigate its continuity. There's another warm-up problem worked out for you so you can have a look at that. I actually did the difference of squares twice. Okay, these are some questions from homework, so feel free to pause, or from your previous night's homework. feel free to pause the video. There's a few more examples of indeterminate limits. These are our notes from yesterday on continuity. Remember, f at a has to be defined. F at x has to have a limit as x approaches a, and the limit has to be equal to the defined height. So step 1 and 2 have to give you the same values. There's an example of a piecewise function that we looked at yesterday. And this is what we're going to look at today. All right, so the job here is to sketch the function first. I showed you yesterday how you can actually determine if it's continuous or determine the points of discontinuity without sketching the graph. Here, it's asking us to sketch the graph first. So I'd just like to go over an example of how to sketch those. All right, this function has 1, 2, 3 pieces. The first piece of the function follows the equation x plus 1 to the power of 2. That is for x values that are less than -1. So keep this in mind. In yesterday's video, we were talking about when to draw open dots and closed dots. The rule is this: if you have a greater than or a less than, you need to write an open dot. If you have a greater than equal to, a less than equal to, or an equal to, or an equal sign, you use a closed dot. So for this first portion of the curve, it's for x values that are less than -1. All right, so that would be like numbers to the left of -1, -2, -3, -4, -5. All right, I am going to start by putting a -1, but I'll use an open dot because I know that it cannot equal -1. Again, why can it not equal -1? Because it just says less than -1. All right, less than requires you to draw an open dot. Now keep in mind, it could be -1.1 or it could be -1.05. All right, that's why I don't just start at -2 or -3 or -4. That should be less. Okay, to figure out the y values on this section of the curve, keep in mind we're using this formula. I'm going to plug a -1 in for x, plus 1 gives me 0 squared, 0. The next point would be -2 goes in for x, plus 1 gives me -1, -1 squared is +1. A -3 plus 1 is -2, squared gives me a +4. -4 plus 1 gives me -3, and if I square that, I get 9. Now, this is what it would look like. -1, 0, I would go 1 unit to the left, don't go up or down, and I'm going to draw an open dot. -2, 1, that's 2 to the left, up 1. -3, so 1, 2, 3 to the left, up 4. Here we go. Keep in mind these dots would be closed or filled in because it can equal -2, it can equal -3, it can equal -4. 4 to the left, up 9. Wait, 1, 2, 3. Okay, 9 would be here. And I am going to join those with a nice, smooth curve. Not bad, not bad. I'll darken those in. All right, so there's that first portion of the curve. That was for x values that are less than -1. And you could have started like, you could flip these points around, go -4, 9, -2, 1, -3, 4. Sorry, -4, 9, -3, 4, -2, 1, -1, 0. That might make more sense to some of you. Regardless, all 4 points make that section of the curve. The next portion of the curve is for x values between -1 and +1. Now note this says x is greater than or equal to -1, x is less than or equal to +1. So these x values would be a -1, a 0, and a 1. Those are the only 3 points that can go on that. This section, I could have kept going, -5, -6. That's why I drew the arrow on the end. This section of the curve has only 3 x values, -1, 0, and 1. Question is, are they open dots or closed dots? Well, look, it's greater than or equal to -1. Greater than or equal to closed dot. Less than or equal to +1, closed dot. And the 0 would also be a closed dot. Pretty simple calculation here. When x is -1, f of x would be -1. When x is 0, f of x would be 0. When x is 1, f of x would be 1. So let's draw these points or plot these points. -1, -1, that's 1 left, down 1. Closed dot. 0, 0, that's the origin. 1, 1, that's right 1, up 1. Closed dots. Notice I don't join this piece of the curve to that piece. It's a piecewise function. This section would look like that. And that's what my curve looks like. No arrows on the either ends. Okay, that is just a line segment. Finally, my last section. It's for x values that are greater than 1. The formula I will use for this portion of the curve is 2x minus x squared. It's another quadratic section, so it'll look like a portion of a parabola. For x values greater than 1, think of that. 1, 2, 3, 4, 5, 6, 7, so on. All right, how do I exclude the 1 if it's just greater than 1? With an open dot. Okay, so in my chart, I'll write 1 with an open dot next to it. 2, 3, 4. That's probably lots of points. All right. When I fill a 1 in for x, 2 times 1 is 2. 1 squared is 1. 2 minus 1 gives me 1. When I fill a 2 in, 2 times 2 is 4. 2 squared is 4. 4 minus 4 is 0. When I fill a 3 in, okay, perhaps I should be saying 3 squared first. I do my exponent first. That gives me 9. 2 times 3 is 6. 6 minus 9 gives me -3. When I fill a 4 in, 4 squared is 16. 2 times 4 is 8. 8 minus 16, that would give me -8. All right, here we go. 1, 1, that's right 1, up 1. Now, I know it says it's an open dot, okay? But keep in mind that dot is actually still filled in. That green closed dot would take precedence. Why? Because the function is defined, at this point right here on this section of the curve. Next point, 2, 0, that's right 1, 2, don't go up or down. 3, -3, that's 3 to the right, down 3. And 4 to the right, down 4, 5, 6, 7, 8. There it is. I'm going to join these dots with a nice smooth curve, and I'll put an arrow on the end. I'll highlight these dots again. Okay. Even though this dot is open on this portion of the curve, 1, 1 is filled in on this green portion of the curve, so it would remain filled in. That is what your piecewise function would look like. Okay, a quadratic section, a linear section, and a quadratic section. How do I know that? Second degree, first degree, second degree. Now, when it says check for any points of discontinuity and provide a mathematical reason to validate any points where the function is discontinuous, well, let's remember the rules for continuity, or kind of the layman's terms of continuity. We say a function is continuous if you can draw the curve without lifting your pencil. All right? Or we say it's discontinuous at any of the x values where you lift your pencil. So look, if I'm drawing this curve, I'm good. I have to lift my pencil right here to draw that open dot, and I'd have to jump from that open dot down to this green dot to get to this linear section. So where did I do that? I did that at an x value of -1, okay? 1 unit to the left. So the function is discontinuous at x equals -1. Why is it discontinuous at x equals -1? Well, let's remember our rules for continuity, okay? Step 1 is defined f at 1. Is it defined? Okay, well, yes, we can see from the graph that the function does have a defined height. When x equals, sorry, not 1, -1, all right? I would go 1 to the left. Well, there's an open dot at 0 and a closed dot at -1. I would have to choose the closed dot, the defined height. Perfect. So it passes condition number 1 of continuity. Move on to number 2. Number 2 is to check to see if it has a limit. And remember, the limit exists only if the left-hand limit and right-hand limit are equal. All right, well, what's the left-hand limit? Let's see. So I'll put up my little straight edge here at -1. When I approach -1 from the left, so here's -1, there's an x value of -1. The left side would be this red portion of the curve. When I arrive at an x value of -1, what height did I arrive at? What's the height right here? Okay, that height would be 0. So the left-hand limit is 0. Let's check the right-hand limit. Hit that a few too many times. Okay, the right-hand limit, the limit as x approaches -1 from the right of f of x. Well, again, I don't have to move that little green line, dashed line. This is where x equals -1, but this time I'm approaching from the right side, which would be the blue portion, then the green portion. What height do I arrive at when I hit the fence or I hit this line? I arrived at a height of -1. Okay, I was on that green portion of the curve. Does the left-hand limit and right-hand limit equal one another? Does 0 equal -1? No. So the limit as x approaches -1 of f of x does not exist. And because the limit does not exist, we can say the function is discontinuous at x equals -1. That is our mathematical reason. It's discontinuous at x equals -1 because no limit exists at x equals -1. It fails condition number 2 of continuity. Now, this is actually called a jump discontinuity. And that's what our next video will focus on. Continuity. Types of discontinuity. Thank you.